What we're going to look at today is what's known as the Pythagorean trig identities. Mind you, people just normally just call them the trig identities. They don't give the credit where credit's due. I mean, Pythagoras should be given credit. It's his trig identities. Wow, they're not really his trig identities. They just come from using Pythagoras' theorem, to be honest. So, all right, there's our circle on the coordinate geometry plane. If I draw in a triangle, so the circle is of radius 1, our unit circle as it's known, and I've marked in the angle theta there. Now, we know the equation of that circle is x squared plus y squared is equal to 1. Okay? But using trig, we could say, well, y would end up being sine theta because I made the hypotenuse 1. And x would end up being the cosine of theta, again, because I made the hypotenuse 1. If I substitute that into the equation of the circle, I get the first of our trig identities, which is sine squared theta plus cos squared theta is equal to 1. So it does not matter what the angle is. If you find its sine and square it, then you find its cosine and square it, you'll always end up with the answer 1. Now, to get the second trig identity, all we do is divide everything by sine squared. So sine squared over sine squared, cos squared over sine squared, and 1 over sine squared. Well, sine squared over sine squared is obviously 1. Cosine over sine is cotan. If you remember that relationship that tan is sine over cos, so therefore cos over sine must be the reciprocal of tan, cotan, and the reciprocal of sine is cosec. So we get 1 plus cot squared is cosec squared. To get the third one, instead of dividing by sine squared, we divide by cos squared. So now we've got sine squared on cos squared on cos squared, and 1 on cos squared. Well, sine on cos, as I just mentioned, that's tan, so we've got tan squared. Cos squared on cos squared, that's 1. And the reciprocal of cos is sec. So there's the third one. Tan squared plus 1 is sec squared. So basically we have these three trig identities. The nice thing about the three trig identities is they all involve different ratios. So sometimes people go, oh, which one should I use? Well, it's hard to pick the wrong one because sine is only in 1, cos is only in 1, tan is only in 1, and so on. That relationship that I talked about, sine theta over cos theta equals tan theta, whilst it's not a trig identity, it's more a relationship. In some of these problems that we're going to look at, it can be handy to use that relationship to help solve the problem. So, if you like, that's our fourth pretend identity. Okay. I put this question in here because most textbooks put questions like this along with trig identities. Personally, I don't use trig identities to do it. I think it's a waste of time. The way I would solve something like this, if you've got cos theta is equal to 3/4 and they've told us tan theta is negative, find sine theta. So I'd draw myself up a triangle. And so, okay, I know the cosine of this angle is 3/4. So by Pythagoras, I can work out the other side is the square root of 7. From the information they've given me, I know I'm in the fourth quadrant because they told me cos was positive 3/4. But tan is negative. Well, that's the fourth quadrant. Tan's negative, cosine's positive. That also tells me then that sine will be negative because we're in the fourth quadrant. To get the ratio, I just read off the triangle. Root 7 over 4. So sine theta is negative, in this case, root 7 over 4. What they're probably expecting us to do, because they'd use a trig identity, is say, well, cos theta is 3/4. Substitute it into sine squared plus cos squared is 1, and then go and find sine. But then, of course, you end up with sine theta is plus or minus, because you've got sine squared, and then you have to make a decision about the quadrant. I just think it's more work. I think that's just a lot easier. Draw up a triangle, work out where it is, bang, read off the triangle, there's our ratio. Well, let's look at some actual trig identity problems to solve. This one here, I guess, is a very, very simple one. 1 minus cos squared, they've asked us to simplify it. Now, you probably would be able to look at it and go, oh, I think I know the answer straight away. And if you can't right now, hopefully in a few days or so you will, after you do a few exercises. 1 minus cos squared. Let's pretend I didn't know what the answer is. Hopefully, as I say, it's obvious, but let's see. You'd say, well, what's the trig identity that involves cos squared? The trig identity that involves cos squared is sine squared plus cos squared is equal to 1. So I'm going to substitute in for cos squared. So if I rearrange sine squared plus cos squared is equal to 1, cos squared would equal 1 minus sine squared. And then I can tidy it up. 1 minus 1, and then, oh, it's sine squared. The reality is, I hope after a while we just go straight from, 1 minus cos squared, that's sine squared, because sine squared plus cos squared is 1. But that's how we would go through it if we were unsure. So similarly, with sec squared minus tan squared, again, it's one of those ones where we could be able to look at it and just go, bang, that's the answer. But just imagine we can't. Sec squared, tan squared, trig identity. We've got one that says 1 plus tan squared is sec squared. So I'll replace sec squared with 1 plus tan squared. And, look, tan squared minus tan squared, 1. But again, for one like this, it really is just a rearrangement of the original trig identity. Tan theta, cos theta. So I see something like this, I go, there's no squared. What am I going to do? That's where that other relationship must come in handy. So I'll change tan theta to sine on cos, and then the coses cancel, and I end up with sine theta. Okay. Now the more interesting type. Okay. We want to prove 2 sec squared alpha minus 2 over 4 tan alpha is the same as tan alpha over 2. We are proving this. So just like we saw earlier when we were proving our inequalities, we cannot move terms from side to side. We don't know this is true. We're being asked to prove it's true. So I can work on the left-hand side, prove the right-hand side. I could start with the right-hand side, prove the left-hand side. Or I could work on both sides independently, show they're the same thing. Okay. I've started with the left-hand side. So I've got 2 sec squared minus 2 over 4 tan alpha. Well, the first thing that stands out to me is 2 goes into everything. That's an easy cancelling. But the other thing I see is the sec squared. Well, the trig identity that involves sec squared, 1 plus tan squared is sec squared. So I could substitute that in. And I end up with 2 plus 2 tan squared minus 2. 2 minus 2, that cancels. 2 tan squared on 4 tan. 2 cancels with the 4. Tan alpha on 2. Now you might think, gosh, you put a lot of steps in there. The thing is, when you're trying to prove something, you don't want to be accused of fudging. Okay? So, if I just went from, say, this first step to the last step, they're going to go, well, how the heck did you jump from there to there? And if you did jump that far, then you'd probably write an explanation down why you could jump that far. But if you don't have an explanation, they might think, well, they've just written the answer down because they knew what it was going to be, but did they really know how to get there? So be careful not to leave out too many steps. Okay, don't try and do too much in one step. So there we go. When proving the trig identities, as I say, start with the left, prove the right. Start with the right, prove the left. Work on the left and right independently, show they're the same thing, but never ever solve it like an equation. Because if I was allowed to do that, I could prove anything I like. Because if I start with that equals that, you know what I'm going to do? I'm going to multiply both sides by 0. Multiply both sides by 0, I get 0 equals 0. That's true. Done. Proven. And that's not a valid proof, obviously. Okay. Wow. Exercise jolly good fellow. Outstanding. Exercise jolly good fellow.